All right, I know we've got a slew of equations that we've dealt with, but you know what you're thinking? I know what you're thinking. What you're thinking is, could we double that number of equations? And I'm going, yeah, we can.
Oh, yeah.
All right, so far we've pretty much dealt with linear, also known as translational motion. I think I've only referred to it as linear or just left it off. If I say momentum without any qualifier, it's assumed linear momentum, as opposed to the other type of momentum, which is angular or rotational. Now, just like if you use linear momentum or translational momentum, physicists would know what you're talking about. Tradition has it, it's generally called linear momentum. You generally talk about angular momentum instead of rotational momentum. However, people know what you're talking about. Yeah, everybody, anyone on the street, if you talk about angular momentum, they would understand rotational momentum just as well. So for each of these, there is an analog over there. So if I talk about acceleration, and we're talking about vector stuff here, but the same goes for the scalar. The rotational equivalent is called angular momentum. Sorry, angular acceleration. Now the symbol over here for acceleration is A. Over there, typically it's not 100%, it's only an 80% rule at this point. Angular acceleration, you use the Greek letter, alpha. And typically it is, what is the Greek letter most closely associated with the US customary? The Latin script, what's our alphabet called? Besides the alphabet?
One that makes no sense.
Okay, that one. Really?
Yeah.
So it's either the Greek equivalent or, let's see, that starts with an L, so what Greek letter starts with an L? That. Velocity. V. Anyone want to take a wild guess what that's called over there?
Angular velocity.
Yes. And the letter they chose to use is the omega. It is not a W. So that's omega, it's a lowercase. That's an alpha.
Is this the same as angular speed?
Angular speed, you drop the vector sum, simple.
Oh, okay.
Because when we did centripetal acceleration and we had the omega show up there, yeah, that same omega. Displacement. Whatever letter we happen to be using right now, we'll just go R for now. The rotational equivalent or analog.
Angular displacement.
Although it's usually not called that, angular displacement is fine, so I'm going to write that down. However, rarely are you actually asked to find angular displacement via delta with a theta, phi are the two most common ones. There are a lot of choices along you to find it.
What else would it be called?
Angle, but that gets a little bit sketchy. It's generally a wheel is turning through what angle does it turn? That is asking for angular displacement. And then position. And this is called angle. And that's why some of the language gets a little bit confusing there. But if you have an action happening as if this set of, at what angle is the object, that would be position. Through what angle does the wheel turn? That would be angular displacement.
Is position always R?
No, I use X, R, Y, Z, S. Those are the most common ones I've seen. All right, so that's well and good. However, there are others. Force. Anyone happen to know?
Angular force?
It is not. An influence which might cause a twist or turn.
A force with an angle. Force angle.
Torque.
Torque.
The symbol traditionally used for torque is the tau. Oh, this is the theta, by the way. Let's see, you're good on that one. Tau, and this used to be my most obscure reference, but at this point I've had two students understand the reference. I will refer to sometimes as G2 Kabuka, and I will not explain why.
Can you say what that is? Or will you say what that is?
Who he is?
Oh, it's a person? A
Yes.
name? Okay.
Mass. There is a rotational equivalent to mass. So mass is, in essence, if you think of mass as a resistance to change, the greater the mass, the greater the inertia an object has. If you're dealing with the resistance to rotate, that is known as moment of inertia. It is also referred to as rotational inertia. I tend to call it moment of inertia, thinking more of rotational inertia as a concept, but some textbooks are now moving towards rotational inertia. If you ever see moment of, or the word moment in reference to engineering or physics, and this is not momentum, but moment, it generally is referring to some sort of rotation going on. Momentum.
Is there a symbol for moment of inertia?
Oh, yes, there is. It is a capital I. It's a scalar, as masses. Momentum, angular momentum. And the symbol traditionally is an L. Let's see, what if I left? Oh. Time. What is the rotational analog of time?
Time.
Yes, it is.
Angular time.
It turns out that the time it takes for an object to rotate is the exact same thing as the time it takes for an object to move in a straight line.
No.
Time is the same. It's true. True story. Now,
Are we talking about
non-relativistic.
time as in?
As in time.
Yes. As in the thing that marches on, the thing that flies, the thing that waits for no man.
I see.
It might wait for women, I don't know. All right, so I've given you a bunch of stuff there, and you're going, okay, great, but you haven't really doubled the number of equations. Huh. Yes, I have. All right, so let's take one of the cake formulas, delta x, or s, or r, or y, or z, whichever letter you're using at the moment, is equal to VIT plus 1/2 AT squared. Formula that all of you know and love. And if you did not realize that you loved it, you do now. The rotational equivalent of this, or analog of this, is, well, I just substitute, it's transliteration. Instead of x, I put in theta. Instead of v, I put it in omega. Time, still time, plus 1/2 alpha t squared. And we have our angular cake. Constant angular acceleration, so I guess it's the cake formulas.
Well, that's not as pretty as our first one.
No, it's not.
So that's
It's the Dutch spelling.
is it the, what are you finding with that equation?
All right, so, let's just start out with a linear one. A car has an initial velocity of positive 4 meters per second. It accelerates, the semicolon there, it accelerates at 3 meters per second squared for 10 seconds. How far, or how far what is the car's, period, what is the car's displacement? Over that 10 seconds. All right. A 1A kind of problem, where you've got displacement, initial velocity, final velocity, acceleration, and time. You got the 5 big ones there. And I know that this is 4 meters per second. Acceleration is 3 meters per second squared, and time is 10 seconds. You're asked to find this. And so then you run through your list of cake formulas. The one that does not have VF in it is that one, and it becomes plug and chug. So my displacement will be 4 times 10 plus 1/2, 3, 10 squared, which is 40 plus 75, or 115 meters, assuming I didn't make a careless mistake. So, classic problem. I guess, Jack, you started to solve on this one. You're good with this far?
Yeah.
Okay. A wheel has an initial angular velocity of positive 4 radians per second. It accelerates at 3 radians per second squared for 10 seconds. Through what angle does the wheel rotate? Over that 10 seconds. Under 15 radians. The math is identical to what we just did. But instead of x here, this is theta. Instead of v, it's omega, omega, alpha, and time.
So,
Radians.
we figured out in the second problem how many times it rotated in 10 seconds?
Yes. The wording is, if I said, how much does it rotate, you could give me the answer revolutions, which is not real. I guess you could make an argument that that's an angle unit, but traditionally not.
Well, most of the time it'll be revolutions per second
Radians per
or
second.
radians per second. Yes.
Yeah. Well, yeah, when you start to getting into this, you tend to deal with radians. Radians is the preferred SI unit.
Okay.
And we've done radians, right? We've talked about radians? Okay, I got some subtle nods.
Questions here before we just hit a couple other equations? We will not do them all. All right. P equals mv. What does L equal?
Angular momentum.
Yes. What's the formula?
Oh,
And just as there's conservation of momentum, there's conservation of angular momentum as well. So at that point, we now have three conservation laws: energy, momentum, angular momentum. And again, when I say just plain old momentum, I mean linear. The total force is equal to mass times acceleration. What's the rotational analog? And again, this is total force.
oh, you really have doubled it.
I alpha. Or,
What equals I alpha?
torque.
Okay.
So
So the total torque is equal to the moment of inertia times alpha.
Oh,
Now I recognize that all I've done is talk about, there's two terms in here that we really need to delve more detail on. One is torque and the other one is moment of inertia. And the other one is, what is the direction of angular velocity? We just happen to have a wheel right here.
wondering when we were gonna use that.
All right. So, will you agree that it is spinning?
Yes.
All right. So therefore, it has an angular velocity of not zero. What is the direction of the angular velocity? You say counterclockwise? You think?
Wait, I don't know my
Um, I'm just taking a guess here, but I want to say it's like centripetal motion and it's always going towards the middle.
No, actually, that ultimately that would be more confusing if that were the case, but that would be very simple at this point. All right.
That way,
Why that way?
because it's that way.
Isn't it spinning that way?
Does it, I guess,
360
It is
degrees.
clockwise.
So that's the same?
Now it's some degrees.
All right, there was another speculation? This price is still going. All right, so first off, in terms of clockwise, counterclockwise,
oh, clockwise.
oh, it was counterclockwise to me.
So it's just
Is it?
oh wait, it's a perspective thing.
Ah, okay, so if we went clockwise, counterclockwise, no, there isn't ultimately a correct answer. But if we did clockwise, counterclockwise, we do run into that perspective thing because, you know, which way is the wheel spinning? Well, if you're in the middle of the room, it's clockwise. Sorry, in the middle of the room facing the board, it's clockwise. That's a whole lot of writing to do. That's just too much.
Physicists would have enough.
That's darn straight. They have enough other stuff.
Indeed so.
So, they came up with an idea. Who's left-handed in here? All right, this is directed at you. I'm about to talk about the right-hand rule. It is not the dominant hand rule. Now, you have not done anything to indicate that you would make that mistake, but I've had a number of left-handed people in the past who keep just wanting to go to their dominant hand, and they're backwards. Their answer is backwards.
What?
Okay, so the right-hand rule. Right-hand rule. As it's spinning this way, basically my thumb is the axis of rotation. This is the axis of rotation right here. I'm holding onto it. My thumb is the substitute for the axis of rotation, so I'm either pointing towards the board or away from the board. I want my fingers to curl the way that this is spinning. So if my thumb is pointed this way, well, my fingers curl opposite the direction of the spin. So I want to point towards the board with my fingers curling in the direction that it goes. My thumb points in the direction of the vector. So as this is rotating like that, the angular velocity is towards the board. The angular velocity is towards the ground, except for the wobble. So angular velocity towards the board. Angular velocity to the back of the room. So with this convention, it doesn't matter where I'm standing or where you're standing. If I say the angular velocity is to the back of the room, then you know it's got to be pointing in that direction, therefore it would be spinning like that. Ultimately, it is very convenient. Now, when I was first doing physics and I was being told that the angular velocity was towards the back of the room, I struggled with that, trying to figure out what's going to the back of the room. Nothing is, other than the math. It is a mathematical convenience to talk about the angular velocity and angular momentum in this particular case as well, going that way. In order to get it to go that direction, I applied a torque that was also to the back of the room, which caused an angular acceleration to the back of the room, which caused an angular velocity towards the back of the room since it started at rest. If I apply a torque towards the front of the room, since its velocity, angular velocity was to the back of the room, I applied a torque to the front of the room. Therefore, angular acceleration was towards the front of the room. It's going to slow down because angular velocity and angular acceleration were in opposite directions.